Hi there, welcome back to MA211. Let's talk about the Dirac delta function today. So the Dirac delta function is a function, and I sort of have to put function in quotes there because it can't truly be considered a function. We're just going to run with it and treat it like one anyway. Anyway, it's a thing we use to model instantaneous behavior. So for example, suppose I'm thinking about a spring mass damper system, and I hit the object that's on the end of the spring with a hammer. So I've imparted an external force there, but the force was only acting for a really, really tiny little instant of time, right? Now, if I had a function that could describe the force as it acted, right? It could tell me at each time how much force was acting. If I had a function like that, I could set up my ODE, solve the ODE, and then I could give you the motion of the object. We're going to use a Dirac delta function to model that force that that acts over a really, really short, basically instantaneous period of time. Another example, and the one that I'm going to use here, is suppose I have a salt tank system, right? And I go ahead and add salt over a really, really short period of time. I basically dump the salt in, and I instantaneously add salt to my salt tank system. I'm going to, again, use a Dirac delta function to model that rate of salt flowing into the tank. So I want to think about what happens as I add 1 unit of salt to a salt tank, and I add it over shorter and shorter and shorter time periods. So I'm going to get a new PDF out here, and I'm going to draw some sort of crude graphs. So suppose I add 1 unit of salt during 1 second of time. Then if I plotted the rate of salt at which I'm adding salt, I'd be adding salt during the first unit of time, and I'd be adding it at a rate of 1 unit per time unit. So my rate would be 1 here, and then at time 1 it would die off. Okay. So now what happens if I add 1 unit of salt, but I add it during half a second? So I add salt over a shorter period of time, but I add it at a bigger rate during that time, so that I still end up adding 1 unit of salt. So suppose I add 1 unit of salt. Suppose I add it during 1/2 a second. Then the inflow rate would look like this. Here's 1, here's 1/2, here's an inflow rate of 1 unit per second, here's an inflow rate of 2 units per second. So if I add 1 unit of salt during the first half second, my inflow rate will look like this, right? It'll be 2 during the first half second, and it'll be 0 thereafter. And if I add salt during the first quarter second, then my inflow rate would look like this. So here's 1/4, here's 4, here's 2, here's 1. So I'd be adding salt really, really, really quickly, and it would only be for a very short period of time. So what we want to do is continue this process. Imagine what happens as I add salt during shorter and shorter and shorter and shorter time periods. Let's see. So if we add salt during the first epsilon time period. Oops, that's an epsilon there. Then the inflow rate let's see, we're adding time during the first epsilon time period. We add salt during that time at a rate of 1 over epsilon. So it'll look like this. This function gets a name, and this is called delta epsilon. And it's defined again, it'll be 1 over epsilon if t is less than epsilon, and it's 0 otherwise. Now we can go ahead and describe the delta epsilon function. Without issue, we could describe that in terms of Heaviside functions, so we could Laplace transform it if we wanted. So let's see, the delta epsilon function is 1 over epsilon minus 1 over epsilon Heaviside function shifted by epsilon. Okay, now what I want to do is think about this. As I add salt, my 1 unit of salt, as I decrease the time during which I add it, the graph of my inflow rate will start to look more and more and more highly peaked. So we'll always have 0 inflow before time 0. Now as I add my salt over shorter and shorter and shorter and shorter time periods, my inflow rate will get more and more and more peaked. That should be straight up right along the y-axis. And then it's 0 after this very, very tiny little time period. And this function that I've just graphed there has a special name. This is called the Dirac delta function, and it's called just delta of t. And it's sort of defined in this weird way. At time 0, the Dirac delta function is infinity. Oops, I wrote that backwards. It's infinity if t is equal to 0, and it's 0 if t is non-zero. So it's like you're adding all your salt, you're adding your salt at an infinite rate all at time 0. Okay? So what this is saying is that we are adding 1 unit of salt at an infinite rate because it's happening over 0 time. And you're doing it at time 0. Okay, now if you wanted to add, say, 4 units of salt at an infinite rate at time 0, well, if you went back and worked through this, you'd see that you just need to add 4 delta t. Okay, so that 4 is sort of telling you how much salt you're adding at time 0. And if we wanted to add 4 units at time 6, then the function that would describe that is delta t minus 6 times 4 again. Okay, so again, what we're doing is we're using this Dirac delta function. It represents the addition of something instantaneously. So here we're adding salt over 0 time, so the inflow rate has to be infinite at that time. Now, if we gloss over some things, you can read this if you want. You can find out, well, if I want to Laplace transform the Dirac delta function shifted by a units, I'll get e to the negative as when you do that, okay? So now that we know how to Laplace transform the Dirac delta function and inverse Laplace transform it, there's really nothing to solving ODEs that have Laplace transforms and inverse Laplace transforms in there. What I want to do is talk about how do we use the Dirac delta function to set up ODEs. Okay, so here we have a salt tank. It contains 100 liters of pure water at time 0. Salty water begins flowing into the tank at 2 liters per second. The incoming liquid contains a 1/4 kilogram of salt per liter. The well-stirred liquid flows out of the tank at 2 liters per second. Okay, so let's just model this with a first order ODE. So there's nothing strange going on here. This is dA dt is rate in minus rate out. The rate of salt flowing in is going to be what? 2 liters per second times a 1/4 kilogram per liter. And the rate out will be the concentration of salt in the water, which is A over 100 times 2. So that's going to be what? This is 1/2 minus 1 over 50 A. So that's the ODE that you would get if for that setup. Now let's suppose that at time 20 seconds, 5 kilograms of salt is instantaneously dumped into the tank. Let's see. So what do? Well, our rate in is going to be what? Well, you'll have the normal inflow rate. So we'll have our 2 liters per second times a 1/4 kilogram per liter. Plus at time 20 you have this extra salt flowing in. So you'll have this salt being added instantaneously, delta times t minus 20. And how much is there? There's 5 units. So that's our inflow rate. Our outflow rate stays unchanged. So we end up with something like this. dA dt equals 1/2 plus 5. Oops. And then you'll have a minus 1 over 50 A. Okay. And that's all there is to this. Notice that this guy is a delta function. It's not a Heaviside function. And people always get confused about when do I use a delta, when do I use a Heaviside. So what's happening here? You're adding the salt instantaneously. So the inflow rate would show this big spike, but after time 20 the inflow rate would go back to normal. Okay? With a Heaviside function, Heaviside functions are for things turning on and staying on for a while. So if our inflow rate had gone from a 1/4 kilogram per second to, say, 5 kilograms per second at time 20 and it just stayed on, then we would need a Heaviside function. So if our inflow rate looked like this we would need Heaviside. But that's not what we have. Our inflow rate at time 20, so we have a 1/4 kilogram per second. At time 20 we add all this salt, so our inflow rate will be huge there, and then it dies off. So this is Dirac right here. Okay, let's see. Let's take a look at this next one. So suppose we have a bank account in which I have P of t dollars at time t. If the account pays a constant interest rate R, and you deposit money at the rate F of t dollars per unit time, then P of t obeys this guy. Okay? So remember, F of t is the rate at which I'm adding salt. Or not salt, money to my account. Okay? So, suppose I start at time 0 with $1,000, so P at time 0 is 1,000. The interest rate is 0.05, and suppose I make lump sum deposits of $1,000 at time 1, 3, and 5. How much money will I have after 10 years? Well, we can see that we'll have P prime is going to be equal to 0.05, so 1/20th times P plus F of t, and F of t, again, that's the rate at which I'm adding money. So what's F of t look like? I'm not adding any time or any money other than at times 1,000 or at times 1, 3, and 4. So here's time 1, here's time 3, here's time 4. I'm adding no money at these times, but at time 1 I make a lump sum deposit, so I add a whole bunch of money instantly. So the rate at which I'm adding money is going to be infinite there. The rate at which I'm adding money at time 3 is infinite. The rate at which I'm adding money exactly at that instant 4 is infinite. So these are going to be represented with Dirac delta functions. Now, I want to add $1,000 at each of those times, so my f of t is going to be 1,000 times delta t minus 1 plus 1,000 delta t minus 3 plus 1,000 times delta t minus 4. So here's my differential equation. P prime is going to be 1 over 20 p plus 1,000 times delta t minus 1 plus delta t minus 3 plus delta t minus 4. Okay, and that's it. All right. So let's look at another one. We have a spring mass system. It has mass 1, damping constant 4, spring constant 5. At time 0, the mass is at rest and in the equilibrium position. And at time 2 seconds, an impulsive force with total impulse 6 kilogram meters per second is applied to the mass. Model the situation with a DE. And, well, we won't actually solve it, but you could certainly easily solve it. So we're certainly going to have something that looks like this. We'll have y double prime plus, what's my c, 4y prime plus 5y equals the external force, f of t. And when I say an impulsive force, I mean something that looks like this. It's 0 at all the times other than time 2, and it's like it's an impulsive force, so it just acts over this 0 amount of time. It acts instantly at time 2. So once again, here at time 2, our force looks like that. And it has a total impulse 6, so my f of t is going to be 6 times delta t minus 2. And that's it. Okay, so before we conclude this video, I just want to do a little conclusion or a little differentiation. Remember, Heaviside functions something changes and stays changed. Dirac delta functions something is temporarily infinite. Just for one instant. So something happens instantaneously. So the graph of a Heaviside function, you should be thinking of the graphs of the functions you want to represent. Again, something will have a certain value, and then after that it'll have some other value. A Dirac delta function, something will have some value, it'll turn infinite for a second, and then be back to its original value. So these are the two kinds of graphs you need to be thinking about. And that's it.